We present tunable convolutions with parametric multi-loss optimization. Most image restoration problems are ill-posed and admit an infinite number of valid solutions. Neural networks, however, produce only a fixed type of solution, completely determined by the data and loss function used during training. For example, a super-resolution network trained with an L1 loss generates accurate but less detailed results, while the same network trained with a perceptual loss generates results that are visually more pleasing yet less faithful to the input. A natural question then is, where is the optimal balance? In practice, such balances are not a fixed point, but instead often depend on various external factors, such as user preferences or task-specific settings. We introduced tunable convolutions, a novel layer allowing users to explicitly change network behavior at inference time without requiring any model retraining. Our method is based on an arbitrary number of kernels and objectives, which are jointly optimized through a set of tuning parameters. At inference time, these parameters then become additional model inputs, enabling neural networks to smoothly and reliably transition across differing behaviors in an interactive way. We firstly briefly discuss related work on controllable neural networks. One idea involves modulating all internal features using an interactive condition vector, which is trained to represent the degradation characteristics present in the input, such as the amount of noise or blur. However, this model is not trained on all possible combinations of input images and conditions, thus it may generate artifacts. Alternative previous work instead uses a second tuning branch to modulate features found in the main network branch. Firstly, the tuning branch is disabled and the main branch is trained on one objective. The main branch is then frozen while the tuning branch is trained against a second objective. We note that this strategy is limited to 2 objectives and also approximately doubles the complexity of the overall system. Finally, we review deep network interpolation work. The main idea here is to independently train multiple copies of the same network against differing objectives. Then, at inference time, the pre-trained network parameters theta of each network are linearly combined with a set of interactive alpha weights. The approach offers no guarantees on the correctness of the interpolated theta and may thus lead to suboptimal performance in intermediate regimes. In this work, we propose to control neural networks using a parametric tunable convolutional layer, which includes a set of p different kernels k that are optimized against an equal number of losses L. Our key insight is to explicitly connect each kernel to a different loss objective through a shared set of p parameters omega. Specifically, we use an identical omega to drive the interpolation of the p kernels in each layer and the p objectives in the loss. For increased expressiveness, we use an MLP layer inside each tunable convolution to map the input omega to layer-wise kernel interpolation weights alpha. During training, the parameters omega are sampled at random to explicitly optimize all possible combinations of tuned kernels k hat and tuned losses L hat. This results in an ability to disentangle the effect of each objective into a corresponding kernel. During inference, the parameters omega then become interactive model inputs, enabling users to reliably and consistently control model behavior. We conduct extensive experimental evaluation on various image restoration problems. Our results clearly show that the proposed method outperforms state-of-the-art controllable neural networks in almost all combinations of input tunable parameters. We even outperform traditional neural networks trained on a fixed objective in some instances. Additionally, our method forms the only tunable strategy that is able to simultaneously offer low computational overhead, smooth and reliable interpolation between objectives, support for an arbitrary number of objectives, and an explicit ability to supervise for all possible linear combinations of objectives. In summary, we have presented the first method usable as a drop-in replacement for traditional layers that enable consistent and reliable tunable behavior of neural networks as shown in the animation on the right. Tunable convolutions with parametric multi-loss optimization. Thank you for your attention. Please check out our paper for further details.